In the remote wilderness of Tasmania, something extraordinary is happening that's sending shock waves through the scientific community. Recent evidence has emerged that's forcing researchers to reconsider everything they thought they knew about one of the world's most mysterious creatures. The discoveries are so compelling that experts who've spent decades dismissing reports are now admitting they might have been wrong all along. But here's what makes this story even more incredible. As scientists race to uncover the truth about these modern-day mysteries, they're also revealing the absolute terror that once ruled Australia's ancient landscape. We're talking about predators so nightmarish that they make today's deadliest creatures look like harmless pets. What you're about to discover will challenge your understanding of extinction, survival, and the raw brutality of prehistoric Australia. The evidence is mounting, the implications are staggering, and the truth is more shocking than anyone imagined. Let me start by telling you about the moment everything changed. In early 2025, a team of researchers analyzing trail camera footage from Tasmania's most remote wilderness areas noticed something that made their blood run cold. Hidden in the shadows of footage that had been sitting unexamined for months was a creature that shouldn't exist. The silhouette was unmistakable, the movement patterns were unique, and the implications were earth-shattering. This wasn't just another blurry photograph or questionable sighting report. This was high-definition digital evidence captured by motion-activated cameras placed in areas so isolated that some hadn't been visited by humans in decades. The footage showed characteristics that matched only one known animal, a species that science declared extinct nearly 90 years ago. The creature in question is the thylacine, commonly known as the Tasmanian tiger. This remarkable marsupial predator was once Tasmania's apex hunter, roaming the island's forests and grasslands for thousands of years. With its distinctive striped coat, powerful jaws, and dog-like appearance, the thylacine was perfectly adapted to its environment. Yet European colonization brought catastrophic consequences that would ultimately seal its fate. When 1800s, the immediately settlers arrived in the early viewed the thylacine as a threat to their livestock. Despite limited evidence that these animals were actually responsible for sheep killings, a vicious campaign of persecution began. The colonial government placed bounties on thylacine heads, offering substantial rewards to anyone who could prove they'd killed one. Between 1830 and 1920, bounty hunters claimed thousands of lives, systematically hunting the species toward extinction. The tragic story reached its climax in 1936 when the last known thylacine died in captivity at Hobart's zoo. The animal, neglected and exposed to harsh weather, perished on a cold September night. With that death, science officially declared the thylacine extinct, closing the book on millions of years of evolutionary history. But here's where the story takes an unexpected turn. Almost immediately after the official extinction, reports began flooding in from across Tasmania. Farmers, hunters, park rangers, and ordinary citizens claimed they were still seeing thylacines in the wild. These weren't just casual glimpses either. Witnesses described detailed encounters, complete with behavioral observations and physical descriptions that matched the extinct species perfectly. For decades, the scientific establishment dismissed these reports as misidentifications, wishful thinking, or outright hoaxes. The consensus was clear. The thylacine was gone forever, and anyone claiming otherwise was either mistaken or lying. This dismissive attitude persisted for generations, with researchers refusing to seriously investigate even the most credible sighting reports. However, a groundbreaking study published by University of Tasmania researchers completely changed the conversation. Led by mammal ecologist Barry Brook, the team analyzed over 1,200 reported thylacine sightings using sophisticated statistical models. Their findings were shocking. The data suggested thylacines might have survived well into the 21st century, possibly as recently as the early 2000s. The researchers developed a rigorous credibility scoring system that weighted sightings based on multiple factors. Reports from trained wildlife observers received higher scores, as did sightings with multiple witnesses or those that included detailed behavioral descriptions. Using this methodology, they identified patterns that strongly suggested genuine thylacine encounters were occurring decades after the supposed extinction. But not everyone in the scientific community accepted these optimistic conclusions. Ecologist Colin Carlson published a contrasting analysis arguing that the species likely vanished much earlier, possibly by the 1940s or 1960s at the latest. This created a fierce academic debate that continues to divide researchers today. The controversy intensified when several pieces of potential video evidence surfaced. Grainy footage from remote areas showed animals with thylacine-like characteristics, including the distinctive rigid tail posture and powerful hindquarter propulsion that marked the species. While skeptics questioned the quality and authenticity of these recordings, supporters argued they represented the first visual proof of thylacine survival. One of the most compelling accounts came from wildlife ranger Hans Narding in 1982. During a routine night patrol in northwestern Tasmania, Narding spotted what he identified as a thylacine just 20 feet from his vehicle. Despite being a trained wildlife expert with camera equipment, the encounter happened too quickly for photographic documentation. The sighting triggered a massive 3-month surveillance operation and a 15-month tracking expedition, though no conclusive evidence was found. The search efforts have been extraordinary in their scope and dedication. Jeremy Griffith and James Malley conducted a 6-year systematic search from 1967 to 1973, establishing camera stations and rapid response protocols across Tasmania's western coastline. More recently, cryptozoologist Richard Freeman has led multiple expeditions into the island's most remote territories, using advanced tracking techniques and conducting extensive interviews with eyewitnesses. These investigations have revealed fascinating details about potential thylacine behavior and habitat preferences. Multiple witnesses have reported hearing distinctive vocalizations described as a series of sharp yipping sounds unlike any known Tasmanian animal. Others have observed tracks and scat that don't match any confirmed species on the island. The challenge facing researchers is immense. Tasmania may be roughly the size of Ireland or Switzerland, but its population density is vastly different. With only 540,000 inhabitants compared to millions in those European countries, vast areas of Tasmanian wilderness remain virtually unexplored. Dense forests cover nearly half the island's terrain, creating countless hiding places where a small population of thylacines could theoretically survive undetected. Recent technological advances have brought new hope to the search efforts. High-resolution trail cameras, DNA analysis techniques, and sophisticated tracking equipment offer unprecedented opportunities to document elusive wildlife. Environmental DNA sampling can detect species presence from water sources or soil samples, potentially providing proof without direct observation. But the story doesn't end with Tasmania. Remarkably, the majority of reported thylacine sightings actually come from mainland Australia, where the species supposedly vanished over 2,000 years ago. This geographical paradox has created additional layers of mystery and scientific debate. The most scrutinized mainland evidence includes the Doyle footage from South Australia, captured in 1973. This brief 8-millimeter film shows an unidentified animal crossing a road with several characteristics matching thylacine morphology. Despite modern AI enhancement attempts, the footage remains frustratingly inconclusive, though anatomical analysis has identified intriguing details like the low heel placement typical of thylacines. Professional tracker Kevin Cameron added to the mainland mystery in 1984 when he captured photographs allegedly showing a thylacine digging in Western Australia. These images have faced intense scrutiny, with critics pointing to inconsistencies in shadow placement and the absence of key identifying features like the rigid tail or distinctive head shape. The mainland sighting reports have generated three primary theories. First, witnesses might be misidentifying other animals, particularly in poor lighting conditions or at distance. Second, relict populations could have survived in Australia's most remote wilderness areas, hidden from human contact for millennia. Third, historical translocation might have occurred, though no official records support the movement of thylacines from Tasmania to the mainland. A particularly intriguing development emerged in 2021 when researcher Neil Waters released photographs allegedly showing a family group of 3 thylacines. The images generated intense debate, with some experts assigning a 70 to 80% probability of authentic thylacine identification. However, other specialists suggested the subjects were more likely Tasmanian devils, highlighting the ongoing challenges in definitive species identification from photographic evidence. The search has even extended beyond Australia's borders. Forrest Galante's research into a 1960 archaeological discovery of thylacine remains in New Guinea has opened entirely new possibilities. While the species presumably disappeared from New Guinea around 12,000 years ago, the island's vast unexplored territories could theoretically harbor surviving populations. This New Guinea hypothesis gained credibility from the 2016 rediscovery of the Highland wild dog, which had been unseen for 4 decades before researchers confirmed its continued existence in remote mountainous regions. If a large predator could remain hidden for so long in such terrain, perhaps thylacines could have achieved similar survival in isolated ecosystems. The implications of these discoveries extend far beyond academic curiosity. If thylacines have indeed survived into the modern era, it would represent one of the greatest conservation discoveries in history. It would also force a complete re-evaluation of extinction science and species recovery efforts worldwide. Meanwhile, parallel research efforts are pursuing an entirely different approach to thylacine restoration. Since 2017, scientists have achieved complete genome sequencing of thylacine DNA, creating the most comprehensive genetic blueprint of any extinct species. This breakthrough has attracted major investment in de-extinction research, with the goal of potentially recreating thylacines through advanced genetic engineering techniques. The de-extinction project faces enormous technical challenges and could require decades to achieve success. However, it creates the fascinating possibility that laboratory-created thylacines might emerge before wild populations are confirmed to still exist. As researchers continue their search for living thylacines, they're also uncovering the incredible story of prehistoric Australia, a landscape so dangerous and dominated by massive predators that it makes today's wildlife seem tame by comparison. The Australia that existed tens of thousands of years ago was a realm of absolute terror, where survival meant facing predators so monstrous they would haunt your nightmares. Picture a landscape where every shadow could conceal death, where the very ground trembled under the weight of creatures that dwarfed anything alive today. This wasn't just another prehistoric ecosystem. This was nature's most brutal experiment in creating the perfect killing machines. At the apex of this nightmare food chain prowled megalania, a monitor lizard so massive it redefined the concept of terrestrial predation. Imagine encountering a Komodo dragon, then multiply that terror by 10. Megalania stretched over 25 feet in length and weighed as much as a small car. But size was just the beginning of its horrifying arsenal. This colossal reptile possessed venom glands that would make a cobra seem merciful. Unlike a snake's quick-acting neurotoxin, Megalania's venom worked as a biological torture device. The anticoagulant compounds prevented blood from clotting, ensuring that even a glancing bite would result in continuous bleeding. Victims would slowly weaken as their life force drained away, unable to heal even minor wounds. The hunting strategy of Megalania was particularly terrifying. Like its modern Komodo dragon relatives, this prehistoric monster would ambush prey from concealment, delivering a devastating bite before retreating to safety. The venom would do the rest, tracking the weakening victim until it collapsed from blood loss and shock. No creature, no matter how large or powerful, could escape the inevitable death sentence of a Megalania encounter. But the nightmare didn't end with giant lizards. The skies belonged to equally terrifying predators that ruled from above. Dromornis, known as the Thunderbird, stood over 10 feet tall and weighed more than a grand piano. These weren't ordinary birds. They were feathered death machines equipped with massive beaks capable of crushing bones like twigs. Scientists continued to debate whether these giants were herbivores or carnivores, but their physical capabilities tell a chilling story. Those enormous beaks could have easily torn through flesh and shattered skulls. Their powerful legs, armed with razor-sharp talons, could deliver kicks strong enough to cave in a human chest. Even if they primarily ate plants, any creature foolish enough to threaten a thunderbird would face swift and brutal retaliation. The terror extended to Australia's waterways and shorelines, where Quincana patrolled as the ultimate land crocodile. Unlike modern crocodiles that spend most of their time in water, Quincana had evolved for high-speed terrestrial hunting. Its elongated legs allowed for pursuit speeds that would make a racehorse seem sluggish. Picture a 20-foot crocodile charging across open ground at full sprint, its jaws bristling with teeth designed like steak knives. Quincana's dental arsenal consisted of compressed, recurved teeth that could slice through muscle and bone with surgical precision. A single bite could deliver wounds so devastating that prey would die within minutes from massive trauma and blood loss. The most horrifying aspect of Quincana was its versatility. Unlike specialized predators that excelled in specific environments, this apex hunter dominated both land and water. Early humans seeking safety near rivers and lakes found no refuge from this amphibious nightmare. Whether you stayed on dry ground or ventured into the water, Quincana could follow and destroy you with equal efficiency. Even more terrifying than the giant crocodiles were the massive serpents that lurked in Australia's prehistoric landscape. Wanambi represented the ultimate evolution of constricting snakes, reaching lengths that rivaled modern pythons, but with a killing method far more gruesome than simple strangulation. Traditional constrictors kill by cutting off their prey's breathing or blood circulation. Wanambi took a different approach. Its relatively small mouth opening meant it couldn't swallow large prey whole like modern pythons. Instead, this monster would coil around its victims and then proceed to tear chunks of flesh from their living bodies. Imagine being caught in the crushing grip of a snake thick as a telephone pole, feeling your ribs crack under the pressure, only to realize the real horror was just beginning. Wanambi would methodically strip flesh from bone while you remained conscious, turning every kill into a prolonged torture session. The psychological impact on early human populations must have been devastating. But perhaps the most disturbing creatures were those that seemed familiar, yet hideously wrong. The giant kangaroos of prehistoric Australia weren't the peaceful grazers we know today. Procoptodon stood 9 feet tall and weighed over 500 pounds, but its most terrifying feature wasn't its size. These massive marsupials possessed forward-facing eyes like predators, along with elongated claws capable of disemboweling any creature that ventured too close. While primarily herbivorous, fossil evidence suggests some possessed fang-like teeth, hinting at occasional carnivorous behavior. The idea of a giant kangaroo actively hunting and killing other animals challenges our most basic assumptions about herbivore behavior. Even more disturbing were the giant wombats, known as Diprotodon. Weighing as much as elephants, these creatures possessed bite forces exceeding 11,000 newtons. That's enough pressure to snap a human femur like a dry stick. While they used this incredible jaw strength to process tough plant material, any predator foolish enough to attack would face crushing retaliation. The true apex mammalian predator of this nightmarish ecosystem was Thylacoleo, the marsupial lion. Don't let the name fool you into thinking this was just another big cat. Thylacoleo was something far worse, a killing machine perfected through millions of years of evolution. Pound for pound, Thylacoleo possessed the strongest bite of any known mammal. Its jaws could generate crushing forces equivalent to a lion 2.5 times larger. But the real horror lay in its dental design. Instead of traditional canine teeth, Thylacoleo had evolved massive incisors that functioned like elongated daggers, capable of penetrating deep into vital organs. The killing technique was brutally efficient. Thylacoleo would use its dagger-like incisors to puncture the windpipe, spinal cord, or major arteries, while its blade-like premolars sliced through surrounding tissue. Prey animals that might survive attacks from other predators had no chance against this surgical precision. Death came within minutes, sometimes seconds. Adding to the terror were Thylacoleo's retractable claws and semi-opposable thumbs, features that allowed it to climb trees and drag kills into elevated positions. Imagine looking up into the forest canopy and seeing the silhouette of a 300-pound predator preparing to drop onto your head. No environment offered true safety from this versatile killer. The psychological impact of living alongside these monsters cannot be overstated. Early humans faced predators that could attack from land, water, air, and even from above in the trees. Every journey outside established camps was potentially fatal. Every water source was a potential death trap. Every shadow could conceal something capable of ending your life in the most horrific ways imaginable. Yet somehow, incredibly, humans not only survived in this prehistoric hellscape, but eventually became the dominant species. The story of how our ancestors overcame these seemingly impossible odds reveals remarkable ingenuity, cooperation, and sheer determination in the face of overwhelming terror. The methods they developed to survive weren't just about avoiding predators. Early humans had to become master trackers, understanding the behavioral patterns of creatures that could kill them instantly. They developed sophisticated tool-making techniques, creating weapons capable of threatening even the largest predators. Most importantly, they learned to work together in ways that multiplied their individual capabilities exponentially. Fire became humanity's greatest weapon against the prehistoric nightmare surrounding them. The ability to create and control flames gave early humans their first real advantage over the monsters that ruled Australia. Predators that feared nothing else would retreat from the dancing light and crackling heat of human-controlled fire. But survival required more than just defensive measures. Humans had to become active participants in the ecosystem's brutal dynamics, competing directly with apex predators for territory and resources. This meant developing hunting techniques sophisticated enough to bring down massive prey while avoiding becoming prey themselves. The evidence suggests that human arrival in Australia coincided with the extinction of many megafauna species. Whether this was due to direct hunting pressure, habitat modification, or climate change remains debated. What's certain is that the balance of power shifted dramatically once humans established permanent populations across the continent. The transformation wasn't immediate or easy. Generations of humans lived and died while slowly gaining ground against the prehistoric monsters that had ruled for millions of years. Each successful hunt Each defensive victory, each technological advancement brought humanity one step closer to dominance. The irony is striking. While modern scientists search desperately for evidence that the thylacine might still exist, they're simultaneously uncovering proof of an ancient world where survival itself was miraculous. The creatures that once made Australia a living nightmare have vanished, leaving behind only fossils and our collective evolutionary memory of terror. This prehistoric nightmare world helps explain why the search for surviving thylacines captures our imagination so powerfully. In a landscape once dominated by monsters beyond our worst nightmares, the thylacine represents something almost gentle by comparison. Its potential survival offers hope that not everything remarkable from Australia's past has been lost forever. The evidence keeps mounting in ways that nobody expected. What researchers discovered in early 2025 wasn't just random footage from a single location. Multiple camera stations across Tasmania's most isolated wilderness areas captured similar anomalies during the same time period. The synchronicity is what's driving scientists to reconsider their fundamental assumptions about species extinction. Dr. Sarah Mitchell, a wildlife biologist who spent 2 decades dismissing thylacine reports, found herself staring at footage that challenged everything she believed. The creatures appeared in 3 separate locations over a span of just 5 days, suggesting coordinated movement patterns consistent with a small but stable breeding population. What makes this evidence particularly compelling is the technological advancement in camera trap systems. Modern trail cameras capture ultra-high-definition video with infrared capabilities, eliminating many of the ambiguities that plagued earlier photographic evidence. The clarity allows for detailed morphological analysis that wasn't possible with grainy photographs from previous decades. The behavioral patterns observed in the footage reveal characteristics that match historical thylacine documentation perfectly. The rigid tail posture, the distinctive gait with powerful hindquarter propulsion, and the head positioning all align with museum specimens and early naturalist observations. But it's the hunting behavior captured on camera that's truly extraordinary. One particularly striking sequence shows what appears to be a thylacine stalking prey with the methodical patience that made the species such an effective predator. The animal moves through dense undergrowth with ghost-like silence, pausing frequently to assess its surroundings before continuing the pursuit. This isn't random animal movement. This is calculated predatory behavior from a creature perfectly adapted to its environment. The implications extend far beyond simple species rediscovery. If thylacines have survived undetected for nearly 90 years, it suggests they've developed behavioral adaptations that make them even more elusive than their historical counterparts. They've essentially become phantom predators, existing at the margins of human perception while maintaining viable populations in Tasmania's most remote territories. Multiple indigenous communities across Tasmania have come forward with stories passed down through generations, describing encounters with striped predators that match thylacine descriptions. These oral histories, previously dismissed by academic researchers, are now being re-examined as potential evidence of continuous thylacine presence throughout the supposed extinction period. The cultural significance runs deeper than simple wildlife observation. Traditional knowledge holders describe the thylacine as a spirit guardian of the wilderness, a creature that reveals itself only to those who approach the forest with proper respect. While scientists maintain skeptical objectivity, these cultural perspectives offer valuable insights into potential thylacine behavior and habitat preferences. Environmental DNA analysis has added another layer of intrigue to the investigation. Water samples collected from remote streams in southwestern Tasmania have yielded genetic fragments that show disturbing similarities to known thylacine sequences. While contamination remains possible, the samples were collected from areas that have never housed thylacine specimens or research materials. The DNA evidence creates a fascinating puzzle for researchers. If the genetic material is authentic, it suggests recent thylacine presence in areas where no confirmed sightings have occurred. This possibility indicates that surviving populations might be utilizing territories previously unknown to researchers, expanding the potential search areas exponentially. Acoustic monitoring has revealed another piece of the puzzle. Specialized recording equipment deployed across Tasmania's wilderness has captured vocalizations that don't match any known species on the island. The sounds consist of sharp, repetitive calls with tonal qualities distinct from Tasmanian devils, quolls, or any other confirmed marsupial. Bioacoustic analysis of these recordings reveals frequency patterns and call structures that align with historical descriptions of thylacine vocalizations. Early settlers and zookeepers described a distinctive yapping sound, often compared to a dog's bark, but with unique marsupial characteristics. The modern recordings match these century-old descriptions with remarkable accuracy. The search efforts have intensified dramatically following these discoveries. International research teams are converging on Tasmania with advanced tracking equipment, thermal imaging systems, and sophisticated genetic analysis capabilities. The island has become a focal point for cryptozoological research, unlike anything seen since the search for the ivory-billed woodpecker. But the investigation has also revealed disturbing evidence of human impact on potential thylacine populations. Climate change is altering Tasmania's wilderness ecosystems at an unprecedented rate. Rising temperatures and changing precipitation patterns are transforming the dense temperate forests that might harbor surviving thylacines. Logging operations, despite environmental regulations, continue to fragment potential habitat corridors. Even if thylacines have survived in remote areas, their long-term viability depends on maintaining genetic diversity through population interchange. Habitat fragmentation could doom any remaining populations to slow extinction through inbreeding and genetic bottlenecking. The race against time has created an urgent conservation paradox. Researchers need to confirm thylacine survival without disturbing potentially fragile populations through intensive search activities. Every camera placement, every DNA sampling expedition, every acoustic monitoring installation risks disrupting the very creatures they're trying to protect. Modern conservation science offers tools that weren't available to earlier researchers. Satellite tracking technology can monitor vast wilderness areas for movement patterns consistent with large predators. Drone surveillance provides aerial perspectives that could reveal thylacine territories from safe distances. Genetic analysis can confirm species presence from minimal biological samples. The economic implications of confirmed thylacine survival would be staggering. Tasmania's tourism industry could experience unprecedented growth as wildlife enthusiasts flock to glimpse living specimens of a supposedly extinct species. However, this potential economic boom also represents a threat to any surviving populations through increased human pressure and habitat disruption. International conservation organizations are already positioning themselves to provide funding and expertise if thylacine survival is confirmed. The species would instantly become the world's highest priority conservation target, potentially receiving protection resources that dwarf current endangered species programs. The scientific methodology behind current investigations represents a dramatic evolution from earlier search efforts. Rather than relying on anecdotal sighting reports, researchers are employing systematic surveys using standardized protocols. Camera trap grids cover thousands of square kilometers with overlapping coverage zones that eliminate potential blind spots. Machine learning algorithms analyze thousands of hours of camera trap footage, identifying potential thylacine appearances that human observers might miss. These artificial intelligence systems can detect subtle movement patterns and morphological characteristics that distinguish thylacines from other Tasmanian wildlife. With remarkable accuracy, the psychological impact on the scientific community has been profound. Researchers who built careers on extinction biology are confronting the possibility that their fundamental assumptions about species loss might be incorrect. The potential for thylacine survival challenges core principles about extinction, irreversibility, and conservation failure. Graduate students in wildlife biology are flocking to thylacine research programs, recognizing that confirmed survival would represent the conservation discovery of the century. Universities are establishing specialized research initiatives focused on cryptic species detection and extinction reversal possibilities. The media attention surrounding recent developments has created both opportunities and challenges for serious research. While increased public interest generates funding and volunteer support, it also attracts sensationalist coverage that can undermine scientific credibility. Researchers must balance transparency with the need to maintain rigorous scientific standards. Social media platforms have become inadvertent research tools, with thousands of users submitting photographs and videos from Tasmanian wilderness areas. While the vast majority prove to be misidentifications or hoaxes, occasional submissions provide valuable data about wildlife distribution and behavior patterns. The international implications extend beyond Australian borders. If thylacines have survived undetected for decades, it suggests that other supposedly extinct species might also persist in remote locations worldwide. Conservation biology could be fundamentally transformed by recognition that extinction declarations may be premature in many cases. The search for living thylacines has also renewed interest in de-extinction technology. While genetic engineering approaches continue advancing, the potential discovery of wild populations would eliminate the need for complex laboratory recreation efforts. Natural recovery would be infinitely preferable to artificial resurrection through biotechnology. Meanwhile, the prehistoric context makes modern thylacine survival seem almost miraculous by comparison. In an ancient Australia dominated by creatures that could crush bones with casual bites or tear flesh from living prey, the thylacine represented a more manageable form of predation. Its hunting methods, while efficient, lacked the sadistic brutality that characterized many prehistoric killers. The giant wombat Diprotodon may have been herbivorous, but its defensive capabilities were absolutely terrifying. When threatened, these massive marsupials could deliver bone-crushing blows with their powerful heads. Their thick skulls, evolved for processing tough vegetation, became devastating weapons when defending territory or offspring. Archaeological evidence suggests that early humans occasionally hunted Diprotodon, but such encounters required careful planning and coordinated group efforts. A single mistake could result in fatal injuries from creatures weighing several tons. The courage required to face these giants with primitive weapons defies modern comprehension. The marsupial lion Thylacoleo represented predatory evolution taken to its logical extreme. Every aspect of its anatomy was optimized for killing with maximum efficiency. Its powerful forelimbs could pin struggling prey, while its specialized teeth delivered precise fatal wounds. Nothing in modern Australia comes close to matching its predatory capabilities. What makes Thylacoleo particularly disturbing is evidence suggesting it practiced caching behavior, dragging kills into trees for later consumption. Early humans venturing into forested areas faced the constant threat of encountering cached carcasses that might attract these powerful predators. The psychological terror of knowing that death could drop from above must have been overwhelming. The giant monitor lizard Megalania embodied every nightmare about reptilian predators magnified to impossible proportion. Its combination of size, speed, intelligence, and venomous bite created a perfect killing machine that dominated terrestrial ecosystems. Unlike crocodiles that were limited to aquatic environments, Megalania could pursue prey across any terrain. Recent research into Megalania's probable hunting behavior reveals tactics that would make modern predators seem merciful. The venom wasn't designed for quick kills, but rather for prolonged suffering that weakened prey while preventing escape. Victims would endure hours or days of gradual decline before finally succumbing to their wounds. The psychological warfare aspect of Megalania predation cannot be understated. Surviving an initial encounter provided no safety, as the venom ensured eventual death regardless of immediate escape. This created a climate of perpetual terror, where any reptilian encounter could represent a delayed death sentence. Human survival in this prehistoric nightmare required developing technologies and social structures that could counter threats beyond individual capability. Fire provided the first real advantage against creatures that had never encountered controlled flames. The ability to create light and heat on demand revolutionized human defensive capabilities. Tool development accelerated rapidly as humans faced increasingly sophisticated predatory challenges. Spears evolved from simple pointed sticks to complex weapons with detachable points and throwing aids that multiplied effective range and penetrating power. Each technological advancement represented hard-won knowledge purchased through generations of fatal encounters. The social cooperation required for survival against prehistoric megafauna laid the foundation for complex human societies. Hunting parties needed precise coordination to succeed against creatures that could kill multiple humans simultaneously. Information sharing about predator behavior patterns became essential for group survival. The transformation of Australia's ecosystem through human presence represents one of history's most dramatic ecological shifts. Within a relatively short period, creatures that had dominated for millions of years vanished, while a single primate species established continental dominance. The mechanisms behind this transformation continue generating scientific debate. Whether through direct hunting, habitat modification, or climate interaction, human arrival coincided with the extinction of Australia's most terrifying predators. The irony is that we now search desperately for evidence that one comparatively gentle predator might have survived our transformative impact on the continent. The thylacine's potential persistence offers hope that not everything remarkable from Australia's prehistoric past has vanished forever. In a landscape once ruled by monsters that make modern nightmares seem tame, the survival of this enigmatic marsupial would represent a connection to an ancient world that we're only beginning to understand. As researchers continue analyzing the mounting evidence from 2025's discoveries, they're confronting possibilities that challenge fundamental assumptions about extinction, survival, and the hidden secrets that might still lurk in our planet's most remote wilderness areas. The complexity of Tasmania's current ecosystem makes thylacine survival seem even more remarkable when you consider what these animals would need to thrive undetected. Modern Tasmania hosts a delicate balance of native species that have evolved specific territorial ranges and feeding patterns over thousands of years. Any surviving thylacine population would need to navigate these established ecosystems without disrupting the careful equilibrium that currently exists. Recent ecological modeling suggests that a small thylacine population could theoretically survive in Tasmania's remote wilderness without significantly impacting other species. The island's diverse terrain offers multiple microhabitats that could support different prey bases, allowing thylacines to avoid direct competition with existing predators like Tasmanian devils and spotted-tailed quolls. But here's where the story becomes even more fascinating. The behavioral adaptations that would be necessary for long-term thylacine survival might have fundamentally changed these creatures from their historical counterparts. Decades of avoiding human contact could have selected for individuals with enhanced stealth capabilities and altered activity patterns. Wildlife biologists studying the recent evidence are noticing behavioral traits that don't match historical observations of captive thylacines. The creatures captured on modern camera traps display heightened wariness and sophisticated avoidance strategies that suggest learned behaviors passed down through generations. This isn't just instinctual predator caution. This appears to be culturally transmitted knowledge about human threats. The implications are staggering. If thylacinas have maintained breeding populations while avoiding human detection for nearly 9 decades, they've essentially evolved into phantom predators, perfectly adapted to coexistence with modern human activities. Their survival strategy might have required abandoning traditional territorial behaviors in favor of nomadic lifestyle patterns that minimize detection risk. Environmental pressure analysis reveals another layer of complexity in potential thylacine survival. Tasmania's climate has shifted significantly since the 1930s, with changing rainfall patterns and temperature fluctuations that have altered forest composition and prey availability. Any surviving thylacines would have needed to adapt their hunting strategies to accommodate these ecosystem changes. The genetic implications of long-term population isolation present both opportunities and challenges for researchers. If thylacines have survived in small numbers, they've likely experienced genetic bottlenecking that could have eliminated genetic diversity essential for long-term viability. However, this same genetic isolation might have preserved unique evolutionary traits that could provide insights into marsupial adaptation mechanisms. DNA sequencing technology has advanced dramatically since the original thylacine genome project began. Modern techniques can extract genetic information from increasingly degraded samples, opening new possibilities for detecting thylacine presence through environmental sampling. Hair follicles, saliva traces, and even skin cells left on vegetation could provide definitive proof of survival. The search methodology has evolved into something resembling a military intelligence operation. Research teams deploy networks of interconnected monitoring stations that can track movement patterns across vast wilderness areas. Motion sensors, infrared cameras, and acoustic recording devices create comprehensive surveillance grids that operate continuously regardless of weather conditions. Artificial intelligence systems analyzing this constant stream of data have identified movement patterns that don't match any known Tasmanian species. The algorithms detect subtle gait characteristics and behavioral sequences that align with historical thylacine observations, while displaying novel adaptations consistent with decades of evolution in isolation. International collaboration has brought expertise from wildlife tracking specialists worldwide. Researchers who've successfully located thought-extinct species in other regions are sharing methodologies that could revolutionize cryptic species detection. The thylacine search has become a testing ground for conservation technologies that could be applied to similar mysteries globally. The economic considerations surrounding potential thylacine discovery extend far beyond tourism revenue. Confirmed survival would trigger international conservation funding that could transform Tasmania's entire approach to wilderness protection. However, this same economic pressure could threaten any surviving populations through excessive human interest in habitat disruption. Insurance companies are already calculating potential liability costs if thylacine attacks on livestock resume after species confirmation. While historical evidence suggests thylacines posed minimal threat to sheep and cattle, Modern agricultural practices might create different interaction scenarios that require careful management planning. The legal framework for protecting rediscovered extinct species remains largely untested. Thylacine survival would create unprecedented challenges for environmental law, potentially requiring new legislation that balances species protection with human economic activities. Property rights, land use regulations, and conservation mandates would need complete reevaluation. Cultural sensitivity issues have emerged as indigenous communities assert traditional connections to thylacine conservation. Aboriginal Tasmanians maintain that their ancestors coexisted with thylacines for thousands of years, before European colonization disrupted these relationships. Their traditional knowledge could provide crucial insights into thylacine behavior and habitat preferences. The psychological impact on conservation biology extends beyond simple species rediscovery. If thylacines have survived while officially extinct, it challenges fundamental assumptions about conservation failure and species recovery possibilities. Every extinction declaration from the past century would require reevaluation in light of this potential survival story. Graduate research programs are redirecting focus toward cryptic species detection and extinction reversal methodologies. The possibility that other supposedly extinct species might persist in remote locations has generated entirely new fields of study within conservation biology. Universities are establishing specialized departments focused on rediscovery science. The technological spillover effects from thylacine research are already benefiting broader wildlife conservation efforts. Advanced camera trap systems developed for detecting elusive predators are being deployed to monitor endangered species worldwide. Acoustic analysis techniques are revealing previously unknown vocalizations from threatened wildlife populations. Satellite imagery analysis has revealed potential thylacine habitat corridors that weren't recognized through ground-based surveys. These remote sensing techniques identify vegetation patterns and topographical features that could support small predator populations while remaining invisible to conventional wildlife monitoring methods. The international media attention has created both opportunities and risks for serious research efforts. While increased public awareness generates funding and volunteer support, sensationalized coverage can compromise scientific objectivity and create unrealistic expectations for immediate discovery confirmation. Social media platforms have become inadvertent data collection systems where thousands of users submit wildlife observations from Tasmanian wilderness areas. While most submissions prove irrelevant, occasional reports provide valuable information about wildlife distribution patterns and ecosystem changes that inform broader research strategies. The philosophical implications of thylacine survival extend into fundamental questions about extinction, permanence, and species resilience. If a supposedly extinct species can persist undetected for decades, it suggests that nature's capacity for survival exceeds human understanding of ecosystem dynamics and species adaptation capabilities. Religious and spiritual communities have embraced thylacine survival possibilities as evidence of divine intervention or natural miracle preservation, while scientists maintain secular objectivity. These cultural perspectives contribute to public support for conservation efforts and wilderness protection initiatives. The forensic analysis of alleged thylacine evidence has become increasingly sophisticated as researchers develop new techniques for species identification from limited physical traces. Footprint analysis now incorporates pressure distribution patterns and gait biomechanics that can distinguish between closely related species with remarkable accuracy. Scent detection dogs trained specifically for thylacine odor identification are being deployed across Tasmania's wilderness areas. These specialized canines can detect scent traces that remain undetectable to human observers, potentially revealing thylacine presence through olfactory evidence rather than visual confirmation. The veterinary implications of thylacine rediscovery present unique challenges for wildlife health management. Any confirmed populations would require careful health monitoring to assess genetic diversity, disease susceptibility, and reproductive viability without disturbing natural behaviors through excessive intervention. Reproductive biology research based on historical specimens suggests that thylacines had relatively low reproductive rates compared to other marsupials. Any surviving populations would need careful protection of breeding individuals to maintain genetic diversity and prevent further population decline through human interference. The habitat restoration implications are enormous. If thylacines have survived in degraded or modified ecosystems, it demonstrates remarkable adaptability that could inform restoration efforts for other threatened species. Understanding how they've adapted to environmental changes could revolutionize conservation strategies worldwide. Climate change modeling suggests that Tasmania's wilderness areas will continue experiencing significant environmental pressures over the coming decades. Any thylacine populations would need ongoing habitat protection that accounts for shifting temperature and precipitation patterns that could alter prey availability and territorial requirements. The comparative analysis with other cryptic species rediscoveries provides encouraging precedents for thylacine survival possibilities. Multiple species previously declared extinct have been rediscovered in recent decades, demonstrating that remote populations can persist despite intensive human activities and environmental changes. However, the time scale involved in potential thylacine survival exceeds most other rediscovery cases by several decades. Maintaining viable breeding populations while avoiding human detection for nearly 90 years would represent an unprecedented achievement in cryptic species persistence. The prey base analysis reveals that Tasmania's current ecosystem could theoretically support small thylacine populations without significant ecological disruption. Native mammals, birds, and reptiles provide diverse hunting opportunities that could sustain predators with flexible dietary requirements and adaptable hunting strategies. Territorial range calculations based on historical data suggest that surviving thylacines would require vast areas to maintain genetic diversity through population interchange. Tasmania's wilderness areas might be sufficient to support small populations, but long-term viability would depend on maintaining habitat connectivity across multiple regions. The seasonal behavior patterns observed in recent evidence suggest that potential thylacine populations have adapted their activity cycles to minimize human contact during peak tourist seasons. This behavioral flexibility demonstrates sophisticated adaptation to modern environmental pressures that weren't factors in historical thylacine ecology. Weather pattern analysis correlates increased sighting reports with specific meteorological conditions that might influence thylacine activity levels or visibility. Understanding these environmental triggers could improve search strategies and increase chances of obtaining definitive photographic or video evidence. The acoustic signature research has identified potential thylacine vocalizations that differ from historical recordings, suggesting evolutionary adaptation in communication patterns. These vocal changes could reflect adaptation to changed acoustic environments or social isolation effects on traditional communication behaviors. Genetic drift modeling predicts that isolated thylacine populations would have experienced significant evolutionary changes over multiple generations of separation from historical gene pools. Any surviving individuals might display physical or behavioral characteristics that differ noticeably from museum specimens and historical observations. The conservation genetics implications extend beyond simple species preservation into questions of evolutionary uniqueness and adaptive potential. If thylacines have survived through genetic adaptations to modern environmental pressures, they might represent evolutionary innovations that could inform broader understanding of mammalian adaptation mechanisms. Ecosystem modeling suggests that thylacine reintroduction into broader Tasmanian habitats could have complex ecological consequences that require careful management planning. While they once filled important predatory niches, current ecosystems have adapted to their absence in ways that might create unexpected interaction dynamics. The international conservation community is watching Tasmania's thylacine research as a potential model for cryptic species detection worldwide. Successful confirmation methods could be applied to similar mysteries in remote locations globally, potentially leading to multiple rediscovery events that revolutionize understanding of extinction processes. The technological innovations emerging from thylacine research are already finding applications in monitoring other elusive wildlife species. Camera trap improvements, genetic analysis techniques, and behavioral modeling systems developed for thylacine detection are enhancing conservation efforts for confirmed endangered species worldwide. As evidence continues mounting and research methodologies become increasingly sophisticated, the possibility of confirmed thylacine survival grows more plausible with each passing month. The implications would extend far beyond simple species rediscovery into fundamental reconsideration of extinction science, conservation priorities, and humanity's relationship with the natural world. The story that began with prehistoric nightmares and ancient predators has evolved into a modern mystery that could reshape our understanding of species persistence and adaptation. Whether thylacines still roam Tasmania's remote wilderness remains to be definitively proven, but the evidence suggesting their survival continues growing stronger with each new discovery. The mounting evidence has created an unprecedented situation in conservation biology. Research teams are discovering that Tasmania's ecosystem dynamics might be far more complex than anyone previously understood. The island's remote valleys and dense forest systems could be harboring secrets that challenge everything we thought we knew about predator-prey relationships and species survival. What's particularly fascinating is how the search for thylacines has revealed gaps in our knowledge about Tasmania's current wildlife population. Scientists are finding species distribution patterns that don't match official records, suggesting that even confirmed native animals are utilizing territories and resources in ways that weren't previously documented. The thermal imaging surveys conducted across Tasmania's wilderness have detected heat signatures that don't correspond to any known species on the island. These anomalous readings appear in locations where traditional wildlife surveys have found no evidence of large mammal activity. These patterns suggest creatures with body temperatures and movement behaviors that align with historical thylacine characteristics. Advanced genetic sampling techniques have revealed DNA fragments in soil samples from areas where no thylacine specimens have ever been housed or studied. The genetic material shows degradation patterns consistent with recent deposition rather than historical contamination, suggesting active presence of creatures carrying thylacine-like genetic markers. The behavioral ecology research has uncovered evidence of systematic prey selection patterns in remote areas that don't match any confirmed Tasmanian predator. Kill sites show bite patterns and consumption methods that align with historical descriptions of thylacine feeding behavior, particularly the methodical stripping of flesh that characterized their hunting style. Multiple independent research teams working in different regions of Tasmania have reported similar findings without coordinating their efforts. This convergent evidence from separate investigations strengthens the possibility that genuine biological phenomena are occurring rather than measurement errors or wishful thinking. The cave system surveys have revealed extensive underground networks that could provide shelter and breeding sites for small populations of large predators. These subterranean environments maintain stable temperatures year-round and connect to surface territories through hidden entrances that would be virtually impossible to locate without specialized equipment. Isotope analysis of water sources in remote areas shows consumption patterns that suggest the presence of large carnivorous mammals not accounted for in current ecosystem models. The chemical signatures indicate dietary preferences and metabolic processes, consistent with marsupial predators of thylacine size and feeding habits. The vegetation impact studies have identified browsing patterns that don't match any confirmed herbivorous species in Tasmania. These feeding signs appear in areas where large predators might establish territories, suggesting complex predator-prey dynamics involving species that haven't been officially documented. Seismic monitoring equipment deployed to track wildlife movement has detected vibration patterns consistent with quadrupedal locomotion by animals weighing between 30 and 60 pounds. The gait characteristics recorded by these sensitive instruments match biomechanical models of thylacine movement developed from historical footage and skeletal analysis. The pheromone detection research has identified chemical compounds in certain wilderness areas that don't match any known Tasmanian mammal. These scent markers appear to be territorial indicators used by creatures with metabolic and hormonal profiles, similar to historical thylacine specimens. Satellite vegetation analysis has revealed game trail patterns that suggest regular use by medium-sized predators in areas where no confirmed carnivorous mammals are known to exist. These pathways connect different habitat zones in ways that would benefit hunters with flexible dietary requirements and territorial needs. The underwater acoustic monitoring of Tasmania's rivers and streams has recorded sounds that don't correspond to any aquatic or semi-aquatic species known to inhabit these waterways. The vocalizations occur at frequencies and intervals that match historical descriptions of thylacine communication patterns. Forensic analysis of alleged scat samples has revealed parasites and dietary components that align with carnivorous marsupials but don't match waste products from any confirmed species currently living in Tasmania. The biological markers suggest predators with hunting patterns and nutritional requirements consistent with thylacine ecology. The electromagnetic field studies have detected anomalies in certain wilderness areas that correlate with the presence of large mammals moving through dense vegetation. These readings appear in locations where traditional tracking methods have failed to identify the source of recurring disturbances to local wildlife populations. Weather correlation analysis has revealed that alleged thylacine sightings increased dramatically during specific atmospheric conditions that would favor predator activity while reducing human presence in wilderness areas. This pattern suggests that surviving populations might have adapted their behavior to avoid detection during periods of increased human activity. The comparative skull analysis, using three-dimensional modeling, has identified bone fragments from remote cave sites that show morphological characteristics intermediate between historical thylacine specimens and modern Tasmanian carnivores. These findings suggest possible evolutionary adaptation in cranial structure over multiple generations. Nutritional analysis of prey species in areas with unusual predation patterns reveals stress indicators that typically result from pressure by efficient hunters. The biochemical markers in potential prey animals suggest they're adapting to predatory pressure from creatures with hunting capabilities that exceed those of confirmed Tasmanian carnivores. The Geological Survey data has identified mineral compositions in certain cave systems that would provide essential nutrients required by large carnivorous mammals. These underground environments could theoretically support breeding populations of predators that rarely venture into surface territories where human detection becomes likely. Hydrogeological mapping has revealed underground water systems that connect remote wilderness areas across vast distances. These hidden waterways could provide travel corridors for elusive predators while maintaining access to prey populations in multiple habitat zones without surface exposure. The paleoecological reconstruction based on recent fossil discoveries suggests that Tasmania's prehistoric ecosystems were far more complex than previously understood. These ancient food webs included predatory niches that might still exist in modified forms, potentially supporting relict populations of supposedly extinct species. Biomechanical modeling using advanced computer simulations has demonstrated that thylacine hunting strategies would remain viable in Tasmania's current ecosystem. The prey base and territorial requirements could theoretically support small populations of these predators without significant ecological disruption. The evolutionary genetics research has revealed that marsupial predators possess adaptive capabilities that could facilitate survival in changing environments over multiple generations. These genetic mechanisms might enable rapid behavioral and physiological adjustments that would enhance survival prospects for isolated populations. Population viability analysis using current habitat data suggests that Tasmania's wilderness areas could support breeding populations of medium-sized predators if those populations maintain specific behavioral adaptations for avoiding human contact. The mathematical models indicate potential sustainability even with very small founding populations. The chemical ecology studies have identified pheromone signatures in certain territories that indicate complex social behaviors among unknown carnivorous mammals. These chemical communications suggest sophisticated territorial marking and mate recognition systems that could maintain genetic diversity in small, isolated populations. Behavioral synchronization research has revealed coordination patterns among Tasmania's native prey species that typically develop in response to efficient predatory pressure. These defensive behaviors appear in areas where no confirmed large predators are known to exist, suggesting the presence of unidentified apex hunters. The landscape connectivity analysis has mapped potential movement corridors that could support wide-ranging predators while minimizing human contact opportunities. These natural highways through Tasmania's wilderness could theoretically allow genetic interchange between isolated populations across the island. Trophic-level analysis of Tasmania's current ecosystem reveals energy flow patterns that suggest the presence of apex predators not accounted for in official species inventories. The mathematical models indicate predatory pressure consistent with medium-sized carnivorous mammals operating at population densities below detection thresholds. The reproductive ecology modeling based on historical thylacine data suggests that successful breeding populations could persist with surprisingly small numbers of individuals if environmental conditions remained stable. The genetic diversity requirements might be lower than initially calculated, increasing survival probability estimates. Habitat suitability mapping using current environmental data has identified numerous locations across Tasmania that could provide all necessary resources for thylacine survival. These areas offer appropriate prey density, water access, shelter opportunities, and minimal human disturbance, while maintaining connectivity to other suitable territories. The predator-prey dynamics research has revealed that Tasmania's current mammal populations could theoretically support additional predatory pressure without ecosystem collapse. the introduction of efficient hunters like thylacines might actually restore natural balance by controlling overabundant herbivore populations in certain regions. Genetic rescue modeling suggests that even severely bottlenecked thylacine populations could recover genetic diversity through careful management if rediscovered before complete reproductive failure. The marsupial reproductive strategies might provide advantages for population recovery that aren't available to placental mammals. The conservation prioritization analysis indicates that confirmed thylacine survival would immediately trigger the largest species recovery effort in modern conservation history. The international funding and expertise that would become available could transform not only thylacine conservation, but broader ecosystem protection across Tasmania. Climate adaptation research suggests that thylacines possessed physiological flexibility that could enable survival under changing environmental conditions. Their marsupial metabolism and behavioral adaptability might provide advantages for coping with climate change impacts that threaten other Tasmanian species. The ecosystem services analysis reveals that apex predators like thylacines could provide significant ecological benefits by controlling pest species and maintaining natural selection pressure on prey populations. Their return could enhance ecosystem stability and resilience in ways that current conservation strategies cannot achieve. Territory establishment research indicates that recolonizing thylacines could utilize abandoned territories without displacing existing native species. The predatory niche they once occupied remains largely unfilled, creating opportunities for reintegration without significant ecological conflict. The genetic diversity assessment of potential thylacine populations suggests that even small surviving groups might retain sufficient variation for long-term viability. Marsupial genetics appear more resilient to bottlenecking effects than previously understood, increasing optimism for population recovery scenarios. Social structure modeling based on historical observations indicates that thylacines could maintain breeding populations with flexible social organizations that adapt to environmental pressures. This behavioral plasticity could be crucial for survival in modified landscapes with human presence and altered prey availability. The dispersal capability analysis suggests that young thylacines could potentially recolonize suitable habitats across Tasmania if core breeding populations persist in remote refugia. Their mobility and adaptability could facilitate natural range expansion without human intervention once populations stabilize. Predation impact modeling indicates that returning thylacine populations could provide biological control services that reduce agricultural pest problems while maintaining natural ecosystem balance. Their hunting efficiency could benefit both conservation goals and economic interests through integrated landscape management. The cultural integration research explores how thylacine recovery could strengthen connections between conservation science and indigenous knowledge systems. Traditional ecological understanding could provide crucial insights for managing recovered populations while respecting cultural relationships with country. Population genetic simulation reveals that successful thylacine recovery could provide a model for de-extinction efforts worldwide. The techniques developed for managing recovered populations could inform similar projects for other species while advancing understanding of conservation genetics and population management. The landscape-scale planning research indicates that thylacine recovery would require coordinated management across multiple jurisdictions and land tenure types. This integration could drive improvements in conservation planning that benefit numerous threatened species beyond just thylacines. Behavioral adaptation analysis suggests that recovered thylacine populations might display novel characteristics that reflect evolutionary responses to modern environmental pressures. These adaptations could provide insights into mammalian evolution and behavioral ecology that advance scientific understanding. The ecosystem restoration potential of apex predator recovery could transform Tasmania's wilderness areas by restoring natural selection pressure and predator-prey dynamics that have been absent for decades. This ecological restoration could enhance biodiversity and ecosystem function across the landscape. Food web reconstruction modeling indicates that thylacine recovery could stabilize prey populations that currently experience boom-bust cycles due to the absence of natural predation pressure. This stabilization could reduce human-wildlife conflicts and improve overall ecosystem health. The conservation genetics research suggests that thylacine populations might retain unique evolutionary adaptations that disappeared from captive specimens. Wild populations could harbor genetic variants that provide insights into marsupial evolution and adaptation mechanisms. Habitat restoration priorities would be revolutionized by confirmed thylacine survival, creating incentives for landscape-scale conservation that benefits entire ecological communities. The umbrella species effect could drive protection efforts that enhance biodiversity far beyond single-species recovery goals. The scientific methodology developed for thylacine detection is already advancing techniques for monitoring other cryptic and endangered species worldwide. These innovations in wildlife surveillance and population assessment could revolutionize conservation biology and improve success rates for species recovery programs globally. As research continues and evidence accumulates, the possibility of thylacine persistence becomes increasingly plausible. Whether these remarkable marsupials have indeed survived against all odds remains to be definitively proven, but the mounting evidence suggests we may be on the verge of one of the greatest conservation discoveries in modern history. The implications extend far beyond Tasmania's shores, potentially revolutionizing our understanding of extinction, adaptation, and the remarkable resilience of life in the face of seemingly insurmountable challenges. The search continues, and each new piece of evidence brings us closer to answering the ultimate question. Do thylacines still roam the wild places of Tasmania, waiting to reclaim their place in the natural world? The technological revolution in thylacine research has uncovered patterns that nobody anticipated. Advanced machine learning algorithms processing years of camera trap data have identified movement signatures that don't match any confirmed species database. These artificial intelligence systems can detect subtle locomotion patterns invisible to human observers, revealing creatures moving through Tasmania's wilderness with gaits that align perfectly with biomechanical models of thylacine movement. What's driving scientists to the edge of their seats is the consistency of these findings across multiple independent research programs. Teams working in isolation from each other are discovering similar anomalies in different regions of the island. This convergent evidence from separate investigations eliminates the possibility of systematic bias or equipment malfunction. The acoustic analysis has revealed something truly extraordinary. Specialized recording equipment deployed across remote valleys has captured vocalizations that don't exist in any known Tasmanian species catalog. These sounds consist of rhythmic calling patterns with frequency characteristics that match century-old descriptions of thylacine communication. The recordings occur most frequently during dawn and dusk periods when historical observations suggested peak thylacine activity. Environmental DNA sampling has produced results that challenge every assumption about species detection and survival. Water sources in areas where no thylacine research has ever occurred are yielding genetic fragments that show remarkable similarity to museum specimen sequences. The degradation patterns suggest recent deposition rather than ancient contamination, indicating active presence of creatures carrying thylacine genetic markers. But here's what makes the evidence truly compelling. The behavioral patterns observed in recent footage demonstrate sophisticated predatory strategies that no other Tasmanian carnivore exhibits. Camera traps have recorded systematic prey-stalking behaviors that match historical accounts of thylacine hunting techniques. These aren't random animal movements, but calculated predatory sequences from creatures perfectly adapted to their environment. The cave system investigations have revealed underground networks that could support small populations of medium-sized predators without surface exposure. These subterranean environments maintain stable temperatures year-round and connect to diverse hunting territories through concealed entrances. Thermal imaging surveys of these cave systems have detected heat signatures consistent with mammalian activity in areas supposedly devoid of large wildlife. Isotope analysis of remote water sources shows consumption patterns suggesting the presence of carnivorous mammals not accounted for in current ecosystem models. The chemical signatures indicate dietary preferences and metabolic processes consistent with marsupial predators of thylacine proportions. These findings appear in multiple locations across Tasmania's most isolated wilderness areas. The vegetation impact studies have identified browsing patterns that don't correspond to any confirmed herbivorous species on the island. These feeding signs occur in territories where large predators might establish ranges, suggesting complex ecological interactions involving officially undocumented species. The patterns indicate systematic resource utilization by creatures with specific territorial requirements. Seismic monitoring equipment has detected ground vibration patterns consistent with a quadrupedal movement by animals weighing between 30 and 60 pounds. The recorded gait characteristics match computer models of thylacine locomotion developed from historical footage and skeletal analysis. These vibrations occur in areas where no confirmed large mammals are known to exist. Pheromone detection research has identified chemical compounds in certain wilderness regions that don't match any known Tasmanian mammal. These scent markers appear to function as territorial indicators used by creatures with hormonal and metabolic profiles similar to historical thylacine specimens. The chemical signatures suggest sophisticated social behaviors among unknown carnivorous mammals. The satellite vegetation analysis has revealed game trail patterns indicating regular use by medium-sized predators in areas where no confirmed carnivorous mammals are documented to exist. These pathways connect different habitat zones and configurations that would benefit hunters with flexible dietary requirements and extensive territorial needs. Underwater acoustic monitoring of Tasmania's waterways has recorded sounds that don't correspond to any aquatic or semi-aquatic species inhabiting these environments. The vocalizations occur at frequencies and intervals matching historical descriptions of thylacine communication patterns near water sources where they historically hunted. Forensic analysis of collected scat samples has revealed parasites and dietary components aligning with carnivorous marsupials, but not matching waste products from any confirmed species currently inhabiting Tasmania. The biological markers suggest predators with hunting patterns and nutritional requirements consistent with thylacine ecology. Weather correlation analysis reveals that alleged thylacine encounters increased dramatically during specific atmospheric conditions, favoring predator activity while reducing human presence in wilderness areas. This pattern suggests surviving populations might have adapted their behavior to avoid detection during periods of increased human activity. The comparative morphological analysis, using three-dimensional modeling, has identified bone fragments from remote locations showing characteristics intermediate between historical thylacine specimens and modern Tasmanian carnivores. These findings suggest possible evolutionary adaptation in skeletal structure over multiple generations of isolation. Nutritional analysis of prey species in areas with unusual predation patterns reveals stress indicators typically resulting from pressure by efficient hunters. The biochemical markers in potential prey animals suggest they're adapting to predatory pressure from creatures with hunting capabilities exceeding those of confirmed Tasmanian carnivores. The evidence is undeniable, the implications are staggering, and the truth is more extraordinary than we ever imagined. From the nightmarish predators that once terrorized prehistoric Australia to the mounting proof that thylacines might still prowl Tasmania's remote wilderness, this story challenges everything we thought we knew about extinction and survival. Whether these phantom predators have indeed cheated death for nearly 90 years remains the ultimate question. But one thing is certain: nature's capacity